continuing the proof. Again, what are we proving? We're proving existence of conditional expectation of a random variable, which is almost surely finite and whose expectation is defined. Okay. And what is the conditional expectation? The conditional expectation is another random variable that satisfies these two conditions. And we have already given a proof, and we gave a proof. We spent quite some time discussing details of this proof in case where the random variable x is non-negative and integrable. Okay. And now we're going to consider the case where it is non-negative without making any assumptions about it being integrable. So suppose x is non-negative, finite almost surely. Let's go back here. This is in the statement of the theorem. We need x to be finite almost surely. So suppose x is finite almost surely. It is non-negative, but we no longer assume it is integrable. And then in this case, for x, we can write x as a sum of other non-negative functions which are non-negative and integrable. Okay, so let us emphasize here that each of these xn is integrable. Okay. How can we do that? Well, we can take, for instance, xn to be equal to x if n minus 1 is less than x, and x is less than n, and 0 otherwise. So we're slicing x into bits, and each bit is when x is between two consecutive integers. We take xn to be x in that case and 0 otherwise. So we are decomposing x according to on which unit interval it lies. And then, well, of course, when we sum all these xn's, we're getting x back. There may be other ways to write the x in this way. It doesn't really matter. All that matters is each xn is non-negative and integrable. Yeah, it's a non-negative and integrable. Why that? Because, well, if on the top of non-negative we add integrable, we are in the previous case. So in the previous case, we know that each of these xn's will have a conditional expectation. And we can denote that conditional expectation by Zn for convenience, to have a nice, sensible notation. And we're going to define Z. We are in the proof now. We want to prove existence of Z satisfying two properties. And we're going to now explicitly define Z to be the sum of these conditional expectations of each of these little components of x. And note that Z is also non-negative and is also G measurable. Why? Because each of these xn's, each of these are non-negative and G measurable. So we know we can add them. When we add them, they're still G measurable. And since they are all non-negative, adding all of them, or adding just the first k of them and letting k tend to infinity will give the same. And the second expression is a limit. And we know limit of measurable functions are measurable functions. Anyway, this was just to establish that this function z is indeed measurable and non-negative. Okay, and then using the previous case, what is the previous case? That each Zn is a conditional expectation. So each Zn has this property here. We can substitute Zn by Xn if we are integrating over a set A that is in the sigma algebra G. So this is what we mean by previous case, is that we can replace Zn by xn when we are integrating. So this is when we use it. And using also sigma additivity of the integral, which is what we use here and here, to say that, well, the sum can go inside the integral. When the sum goes inside the integral, the sum over n of all zn's is z, and the sum over n of all xn's is x. And this concludes the proof for this case when the random variable is non-negative but not necessarily integrable. And now the last part of the proof is the general case when we only assume that x is finite almost surely and that the expectation of x is defined. Well, since the expectation of x is defined, we can assume that the expectation of the negative part of x is finite. And now from the previous case, there exist two g-measurable functions. I'm abusing notation a little bit, and I'm calling these z plus or minus. I'm just giving names to these functions using this notation of plus or minus, so I'm a bit abusing the definition here. I'm defining the positive and negative part of a function before defining the function itself. Okay. And they have this property that for every they are G-measurable, and for every set A in the sigma algebra G, their integral will respectively correspond to the integral of x plus or x minus. Okay? So the integral of G plus of Z plus will coincide with the integral of Z minus of Z x plus, and the integral of Z minus will coincide with the integral of x minus. Okay? And well, in particular, if we integrate over the entire set omega, they coincide again, which means Z minus is almost surely finite because its integral is finite on this set on the set omega. Okay. And because it's almost surely finite, well, if it is infinite on a set of measure 0. We can just change its definition on that set of measure 0 to whatever finite number we want, maybe even 0 if we want, because then we can say not only it's almost surely finite, we can say it's surely finite. It's finite for every single little omega in capital omega. Okay, this is the point we want to make here, is that we can assume it is always finite. And now finally, we have defined these two functions, which by abuse of notation, we called z plus and z minus. Now we define z to be exactly the function that has z plus as its positive part and z minus as its negative part, okay, because both of these are non-negative functions. So if we now take the negative part of this variable, it will be z minus, and if we take the positive part, it will be z plus. Okay, this is well defined. Why well defined? Well, when are things not defined in our world? Things are not well defined when we get plus infinity, minus infinity, but we don't need to worry about that because we have just discussed that z minus is always finite. So we're not going to get into this problem. And now for every set A measurable, we can compute, we can expand what will be the integral of this new variable z that we just defined here, what will be its integral on this set A. And well, by definition of integral, it will be the integral of z plus minus the integral of z minus. Now this coincides because z plus is the conditional expectation of x plus, and these will coincide because z minus is the conditional expectation of x minus, and these two will add up to x because this is a property of the integral. This is a definition of integral of a function which is non-negative, is we split into the positive and negative parts. And this will always be well defined because this number is finite and this number is also finite. This concludes the proof of the theorem, and this concludes this video lecture and concludes this unit.